So my name is Deng. I work. Thank you. So I have been in machine learning, voice recognition, image, or multimodal kind of signal processing machine learning for quite a number of years. So it's only about past about 6-7 years since about 2009, I got involved in this deep learning. So when I got into that, I never got back to do anything else. It's such a rich, vibrant area that you may have seen either in this conference or in other conferences that I do encourage everybody to to at least take a very serious look at the trend in this area. And the application areas are exploding, as I'm going to show, perhaps within the next 40-some minutes. So give you a very brief definition of deep learning. So if you go to this Wikipedia, by the way, Wikipedia is very well done. I'm really surprised to see how well it is. Sometimes I look into AI's webpage, and they're so impoverished compared to deep learning. So I think some editors here really are doing some really good job of getting good stuff. So, so deep learning is defined to be it's a sort of general area of a special class of the area in machine learning that has a number of characteristics. And actually take note that this kind of definition and this kind of description of deep learning is actually evolving. So every, over the last 3 or 4 years, I have been given a lot of tutorial in this area. Every time I go to tutorial, I take a look at Wikipedia to see how they change definition. It actually changes every 3 or 4 months. I think somebody may have just love to put things in there. So I think this is the latest version of the definition of deep learning. It actually, but in essence, this is the original definition. I mean, maybe about 10-some years ago. It consists of multiple sort of a cascade of multiple ways of doing nonlinear processing. I mean, this is very generic. It doesn't really say anything about what is neural network or otherwise. But in the narrow sense, it looks like a neural network that everybody think about, right? And that's true. So maybe 80% of kind of work in this area are concentrated on neural network. But there are some other area which could be more important down the road, sort of going beyond the standard neural net, things that you're familiar with, that will play very important role. I'm going to spend a fair amount of time talking about those more forward-looking areas of deep learning. And another extremely important characteristic of deep learning is what's called end-to-end optimization. That actually is the natural consequence of doing this, okay? So many years ago, deep learning couldn't really work well. Like 20-some years ago, neural network people actually also have many, recurrent neural network that has many layers, of nonlinear processing in terms of time. And they couldn't work well because they didn't really know how to do end-to-end optimization. People didn't really understand, how this whole optimization process, was done. Now we have a full, really, really good understanding as to, wow, this one can work. And if you actually look at, today I'll tell you about all the detail about this, just to show you some higher level of, so when I write this article, with more pages, I should be able to give some more insight about this. And another consequence of many layers of nonlinear processing is that it gives you different levels of abstraction of the concept. In terms of data, it's very clear. In terms of image, it's very clear. For different levels, you do have different ways of extracting the important properties of the object. And for speech, it's the same thing happens. So now today's main topic is the different styles of deep learning. So this is what you have seen, probably 95% in the literature. And the remaining part is just showing up, just within the last 1.5 years. So I will actually also concentrate a little bit more about this. And then for those, I'm actually going to try to provide some insight to show you some of the new directions about how reinforced learning style and unsupervised learning style is going to work. And not much really striking results so far yet, especially for this. And there are a lot of good results coming out from here now, just over AlphaGo, for example. And there are very different way of, this is a very different way of thinking about deep learning compared with the deep supervised learning. So for deep supervised learning, essentially, you have the input, you have output clearly. A very complex input-output. For example, the input will be speech waveform. The output will be categories of the words, for example, or the meaning. Now, for the image recognition, the input will be just a pixel as a raw input, and then the output would be just categories of, of the object, for example. And this is very complex. So the key is that you have the paired input. So in the training data, and that goes into the big data here, right? So deep learning requires big data, especially for this area. And then this one is even the demand for big data is even more. This is even more. So everything is big data problem. So this type of deep data says that you have to match input and output. Very expensive. And this style of the learning actually only requires very, very weak teacher. But it requires that the learning machine do a lot of what's called the exploration in order to get the essence out of data. I'm going to show you some examples of this. And deep unsupervised learning is a completely new paradigm. Very active research going on, and then I'm going to show you some preliminary investigation in our team that shows the difficulty of the problem and what kind of direction you're going to go. Okay, so now in terms of big data, essentially I just extract these two lines from the previous slides. So for those of you who actually have been looking into this area, you probably can appreciate the difficulty of this area as well as, let me go back a little bit over here. So here, so let me go. Okay, so here for unsupervised, yeah, this one isn't very clear. I mean, the reason why I gray out is because I'm not going to talk about this, but this is kind of traditional way of thinking about unsupervised learning. When you go to Wikipedia, when you go to textbook, they all talk about the other part. So and these are non-prediction kind of tasks associated with unsupervised learning. But today I'm going to talk about a more important application of unsupervised learning, meaning that you still actually look at the prediction because, in machine learning, about probably 80%, 90% of applications are prediction. And there are other areas like how do you interpret the data, how do you understand data, that's another area. And that area doesn't really seem to have very, very big progress. And deep learning hasn't actually been able to sort of enter into that area. But on the other hand, if you solve this prediction problem in a very subtle way, structured so prediction problem, you actually can make unsupervised learning to make a really, really good practical impact. So that's what I'm going to talk about this. So for deep supervised learning, the input and output data have to be paired. If you don't pair them, you're not going to do anything. I mean, the objective function in deep learning, like cost entropy or whatever criteria you're doing, or mean square error, whatever you're doing for deep learning, really wouldn't even be defined if you don't have the label in the output, if you don't pair them together. I'm going to show you some mathematics to show you that. But this is very costly. Now, for some application, it's not too bad. In the voice recognition, we actually do this pairing. You get a sentence, you say, so like when I say one sentence, we hire somebody to write up exactly what transcription is. You put them as a pair. You put them, maybe millions or millions or billions of samples. You can learn them well, and that didn't happen about 8 years ago, and now we know how to do that. So that's very costly. So it limits a lot of applications other than those big, applications like image. And actually, even for image, it's expensive. Wow. So I remember, so like about 8 or 9 years ago, when we actually did this kind of deep learning, started deep learning at Microsoft. So we have people from, for example, Professor Fefeli, she came over to Microsoft. We talk about, the expense of this, and then people, even with image, saying that, doing the kind of data pairing for image is just not practical at that time, 6 or 7 years ago. And then, the image that came up, when she actually did all this big data that enables all this deep learning to be successful. So that's not bad, but still expensive. Now think about some other applications, like, business analytics. There's so many other applications. This is very important bottleneck. And therefore, it motivates the need to have this, what's called, I call the unsupervised learning, one class, the very important class, which have not been looked at seriously in the past about how to do this unsupervised learning using unpaired input-output data. And that's actually is free, almost. Basically, you can actually naturally find all kinds of this data that has input, output, but they don't have to pair with each other, okay? If you do that, if you can make use of this using so to do this kind of learning using unpaired, low cost, the data to train your predictors, you have to make things very deep. Otherwise, there's just no hope you can do anything. So if you make your architecture deep enough, you have the hope to attack this kind of problem. And that means that your training data is unlimited, which are cheap, no cost. You can do just them, but the only cost is computation. And we know that Moore's law maybe it's not actually there anymore. But the newer generation of hardware would enable that to happen. And that's kind of the way I'm doing. Now I also talk about, so since my title has this artificial intelligence task, so I will actually give you a way of characterizing artificial intelligence in this talk, in the context of this talk. So if you look at the Wikipedia, what's artificial intelligence? It says that it's intelligence exhibited by machine. It's just like artificial intelligence is intelligence that is artificial. It means nothing. Okay. So in my this presentation, I want to define artificial intelligence in a much more concrete term. So it consists of two parts. One part is perception. One part is cognition. So the perception part includes things, the signals, the raw. So the perception related the information that you want to perceive, just like human. Therefore, for speech, you have the input to be the raw waveform, and the output will be text, for example. Now, for video, you will be the video sequences, and then the output could be whatever you want. Either you want to have the story come out of the video, or you want to have whatever other application you might want to do, etc. Now, cognition has much more difficult tasks. So far, deep learning is making big progress in this area. So I'm not going to go. Yeah, actually, in our company, we have been doing quite a number of these applications. So today, I'm just going to concentrate a few the red area. So there is a very wide range of AI application for deep learning. So I'm actually going to give you some summary about something that this part is everybody knows. Okay. So it makes a big huge progress in speech. That happens about 6 to 7 years ago, and our Microsoft happened to be the one that actually started this application in collaboration with our academic collaborators. And the image recognition for about 2 years following this, and a lot of entire CVPR now is actually dominated by image, by deep learning in this area, and natural language processing also started to see about 2 years ago the huge influence of deep learning. So I think ACL conference just happening last week. I mean, it's really dominated by deep learning. And then multimodal, that happens about last year. So I'm going to show you some example of this. And then for information retrieval, I just read this keynote speech by Professor Chris Manning at SIG-IR, and he predicted that after 2 years of this, it's going to be deep learning will probably going to dominate this field. It's not clear. So this traditional field of information retrieval is declining. I mean, not many people are there anymore compared to the previous ones. Whereas in probably KDD or maybe in machine learning, everything is going up, right? And then and this is going down. And he's a professor in natural language processing and also machine learning. Actually, maybe he just want to say it so that people will go there more. But I do think that this one has a big potential. In our Microsoft, we also have seen a lot of progress of deep learning, in this area. And of course, there are lots of other applications which I actually happen to know about, either through my interaction with my friends in various companies or through some media stories that I have learned. So I'm not going to go through all the detail. Okay, so now I'm going to divide the following 30-some minutes to a few topics. One is supervised deep learning speech. So the essence of this topic is that if you use a massive amount of paired input and output big data for training speech recognition using deep learning, it really conquers almost the entire field. The same story will happen to image. So over here, the input is acoustics, and the output will be text. Okay, and then of course at the end of the talk, I will show you exactly how you can expand this paradigm to make that unpaired. That means you can use almost unlimited amount of the data to do the training without really having the cost of pairing them together. So for example, the kind of voice I'm talking about now, once it's done, throw away. The speech recognition won't be able to use what I'm talking about now. Although these are data, right? You have to throw away. But if this paradigm, not this paradigm, but the paradigm I'm going to show, the third paradigm is going to succeed down the road. All this data that I'm using now, without having to have any cost of labeling them, will be able to be useful. Okay, thank you very much. I think more people are coming, so you missed the very important part. Okay, anyway. Okay. Yeah, I know. Yeah, that's. I think. Yeah, sorry. Okay, so I will reflect back a little about this progress about deep supervised learning for speech. That actually dates back about 6.5 years ago, and that actually started with neural NIPS workshop. So we have I worked with Jeff Hinton at that time at Microsoft, and he actually came to our lab. We worked very hard on this speech recognition problem there, and that actually we have this workshop run together where so the people started to see that deep learning begins to make impact. And then I'm going to go through it quick. 2.5 years intensive work within Microsoft. After this, we actually Microsoft created this very impressive demo where so this is Professor Jeff Hinton. This is my boss, Rick Rashid. He's from New York Times. In about 1 month after this big demo, 2012, that's in China, about 3,000 audience. He actually has enough guts to simply stand up like now. He didn't speak Chinese though. He talked English. It gets recognized in English and gets translated in Chinese, and then the synthesizer to speak out in Chinese. And then so Microsoft designed the system for him to talk in such a way that the synthesized voice not only is all correct translation of what he said, but also sounds like himself. And the people actually thought that he would speak, Chinese. No, he said openly he didn't speak Chinese, which I can testify. But anyway, so soon after that, it's a very big impact there. I know we saw that, the audience was shedding their tears, thinking that, wow, now when they talk with their mother-in-law, they don't have to speak, different language. And that's what people said there. And that's that's about 4 years ago. And then the reporter John Markov came to Microsoft to interview. Actually I was interviewed with him, and then I also interviewed with Jeff Hinton. And very important part of the interview is that we both said unconsciously that this technology didn't even get patented. And I think that's one of the reasons why all the companies started. And then he went to Google. We tried to, but anyway, so that. So that's very important. I think I'm really happy that this kind of open source kind of movement in this deep learning really speed up this progress very quickly. But we did actually have some patent there, but not very important patent. Anyway, but when we talked with them, we really just told them that, well, that's not important. I mean, the important thing is that we want to push this area because it's so powerful. So this shows you, this actually, I wrote a book about this whole slides in Springer that was just coming out, and that was Chinese translation for the whole book. So this is not for this audience. Actually, I gave this keynote to this speech audience, about 3,000 people just a few months ago. So that's a slide for expert. But the whole point of this slide to show that there's the publication about this deep learning started in 2009 and all the way until these are the early publications. Now the publication is just massive. The whole conference on the IEEE ICAS is dominated by deep learning, and if you don't do that, automatically you get rejected. So this is the progress that I sort of summarized for this spontaneous speech recognition over the past 20-some years. So this is the error. The lower the better. Okay, like in 1993. The error is almost 100%. Sometimes more than 100%. You know that. I mean, recognition can be error can be more than 100% because if you do sequence structure recognition, if you get insertion, deletion, you add up them, it could be more than 100%. Right? So it's almost 100%. So everything you say is wrong about 20-some years ago. And then people work very hard using, Gaussian mixture model, hidden Markov model, generative model. The error keep dropping very hard, roughly about 20-some%, 26% somewhere. It's about almost 10 years. It didn't really do much. It's some up and down. And then deep learning work that we started in 2009, 2010, just cut the error by 1/3. Just one single technology cut it by 1/3. Now to prepare for Rush's demo, and he became very cooperative. Right? We told him, you say this way, you say that way. He really followed the kind of way that it should make that work. That's why it's demo. Right? And then the error rate dropped down to about, like 7% something. Similar kind of what a human can do. And that's why he said, wow, you can do the demo. Okay, and this is architecture that that our Microsoft actually developed to do this. And also, it's interesting for those of you who are coming from China. You probably know this company, right? It's iFly Tech, and they actually it's probably the most powerful speech company in China. And I mean, in the media, you never see them in US, right? But on the other hand, I just somebody actually emailed so they sent me their annual report. Just about the end of December of 2015, just several months ago. And actually, they mentioned that they started doing deep learning in 2011. So I said, what the heck of it? I have no idea. And I realized I gave a talk about one of the papers there. And actually, I went to the company. It's a university, right? So it's Alta Mata. So I went there to give a talk, and I don't know what it's true. Probably true. They said once they actually, heard our talk here, and they immediately started doing that. So therefore, their history of doing deep learning, speech recognition, probably is earlier than anybody you probably have seen in terms of industrial deployment. That's interesting. So they actually is the first one in China who actually sort of implemented deep learning there. And their system is really, really good, and probably better than most speech recognition in US. And then about 1 year after that, we actually make almost everything practical now. So it's not only in Microsoft product for the voice, but also Google, Siri, Baidu, iFly Tech, they're all using this same technique. Because, the technique is pretty open. It's pretty easy to use. And then this is actually, that was 2004, about 2 years ago. So Microsoft really made that Skype translator to be the product. So if you actually try it, it turned out that you can actually use that very, very nicely, with a very good experience. So again, so this kind of product is actually a testimony that deep learning is entering into mainstream. So let me go through here. So for in the academic world, now people don't publish as much of this deep learning in regular journals. I mean, just go to Nature directly. And this is the original speech paper that I wrote with Jeff Hinton with a bunch of authors. So the title actually is called the shared views of 4 speech groups that includes the big companies together. So this is probably one of the first time all these competitors get together to write papers, to popularize, not only popularize, but also to push this technology into spread in company use. Okay, so I'm going to say just a few words about image recognition. Essentially, it gets shattered by deep learning in the same way, but it started about 2 years later. And this is the similar diagram to the one I show you. But in speech, we get about 20 years of curve, and then it comes down here. And the image is much more recent. I think ImageNet competition didn't happen until just several years ago, 5, 6, 7 years ago. So now before deep learning, that happened in 2012, actually done by Toronto Professor Jeff Hinton's team. Ilya Saskiva and Alice Kwiatkowski, 3 of them. They make a lot of money out of it. So before, the area rate for the shallow model, that Kai Yu from NEC was the one who actually created this sort of benchmark before deep learning took over. And that's why he was so quickly changed to deep learning. So the shallow model roughly about 20-some percent. Actually, just looking at this number, it's just exactly the same number that I show you in speech. So it's very easy for me to talk about, even if I don't work on image directly. The number practically is the same. This is by accident, by the way. This is top five color sigma error rate. And then one single shot in deep learning dropped the error by about 50%. By the way, this is also the number similar to speech number, just one single year. And that happened exactly in the speech. And then the second year, it dropped down to like 11% by this Clarify. And then the third year, I think this number is from Google. And then the fourth year, that was last December, it was announced, actually Microsoft, we have this residual network. It dropped the error down to 3-some percent. So the curve is very similar, and there's a very nice article, several articles about this. I'm not going to get this in Silicon Valley. I'm not going to say too much about this. Now, the depth is of crucial importance. So I took this slide from my, my colleague, Sun Jian. Now he's no longer with Microsoft. And then he actually compared the deep neural network for AlexNet versus this is VGG, and this is the Google Net. They have different layers. And then if you make that, shrink that down, this is 150-some layer. It looks like this deep, this deep, this deep. So it makes original AlexNet that actually make the most impact on, in image become really shallow. So this is real. That's real. And now this kind of work in our company now extended up to about 1,000 layers. It's still working well. It's even better than this. So I'm not going to say too much about this. So I think there's a tutorial in ICML. So my colleague talked about that, and then he actually also left the company. But anyway, so now I'm going to switch to the second style of deep learning, which is deep reinforcement. That's why we are actually hiring very aggressively now. So if you have any passion to do this kind of revolution with us, you come and talk with me. So deep reinforced learning has a very different taste, different way of thinking compared with the deep supervised learning, meaning that essentially you have what's called reinforced learning. That essentially is doing optimal decision making. In the old days, this is also a new paradigm. Just like neural network, it has been around for 40, 50 years. And this is probably about 30, 40 years. Actually, I haven't been in this area until just last about 3 or 4 years, about 3 years. It concerns optimal. It's similar to control theory, if you know electrical engineering. But it's a very different way of thinking because you don't have a good model in the real world, right? So control theory requires that you have good model. Once you have a good model, like robotic, like like airplane, etc., and then you know how to use the Newton's law to model the dynamics, and from that you design the policy to control it, right? And reinforcement is very similar to this, except you don't have the model in the real world. You don't have Newton's law to govern what the business process is, right? So you need to have some learning sort of based approach to solve the problem. But the problem is the same of optimal decision making. And the decision making in control system is that you decide, what kind of force you want to, where you want to, if you want to shoot down the enemy's airplane, where to put your angle to do that. But it's easier problem because, and that's common filter, the solution that gives you the estimate. And then you use control theory to determine exactly what action you want to do. So information is a very different story. So it uses distant and weak teacher as an evaluated award. So in other words, your teacher or whatever symbol labels, it's not something that you want to look afterward because they are not reliable. It just gives you a hint. It's called a reward. Like animal, you train the animal, give a little bit something to eat, and then the mouse is able to follow the maze. So it's similar. It's a very, very weak supervision or teacher. And there is a strong need to do exploration. Otherwise, you are not going to make it work. And that's not needed for supervised learning at all. Now there are more and more important AI applications to come. Deng supervised learning. I'm going to show you for the next slide how to do that. And the whole key point of this slide is to show that before deep learning enters into reinforcement learning, it really didn't work. It's very much like neural network. I mean, in the old days, people try very hard. it didn't really work well. Now, with deep learning, to combine with the reinforcement learning, it really makes this deep reinforcement learning to be one of the state-of-the-art now in solving all these important problems. So the role of deep learning here is not to do end-to-end learning directly to predict your target, but to represent the gigantic state space, which would otherwise not be possible without this deep learning. Okay, so this is important insight. So I'm not going to go through here, and so I really have to credit DeepMind, who actually make this fundamental sort of very impressive progress about what. So this paper was published about 1.5 years ago in Nature, and that actually excited a lot of sort of progress. So the key point is that so because of the use of deep learning, which is very much like deep neural net for speech, it actually makes reinforcement learning from the previously non-working status into the working status in current environment. And that's the model that they use called the DeepQ network. So my time is quick. So and there's another very important paper just coming out about within this year to show that this concept of reinforcement learning combined with deep learning actually can conquer the Go world. And this is the Deng architecture they use. So I just copied from their paper, and then we did some analysis about the 4 kinds of deep neural network in use. It's not just one kind. So for complex problem, you have to use a combination of deep learning technique to make progress, and also they combine this technique with multi-colored tree search to conquer the problem. I'm going to skip all this detail here due to the lack of time. Now, deep learning also make, so this is the paper I just wrote about 1 week ago, about 2 weeks ago with VentureBeat. They asked me to do that. So actually, so in Microsoft, we actually make an announcement that we are actually doing very big effort to do what's called the conversation as the platform. Essentially developing AI, so driven, chatbot, and that make use of deep reinforcement learning. And this is the fundamental technology that drives our bot system. So in my article, I talk about what's wrong, why we need to do chatbot to begin with, what's wrong with app model and what's wrong with the web model. Okay, so now we're entering this mobile sort of era. Now the technology is mature now, and we get tons of data also. And how are we able to make use of this advanced AI technology, including deep reinforcement, to make breakthrough in this area? And then I talk about so I'll refer you if you don't you're interested in this topic. Read some of the things I wrote here, and I also talk about 3 types of the bots in the conversation, and we have to distinguish. We have to have divide and conquer, because directly just saying that let's use the AI technique to do this human-like conversation, I think it's too broad. We have to do kind of divide and conquer, solving different classes of conversation problem, and then we put them all together. And that's kind of the whole point. And this is a very high-level description about our strategy. Now, I want to have one note about deep reinforcement and deep supervised learning, paradigm 1 and 2. And for those of you who actually go into details about DeepQ network, so for those of you who are doing structured supervised learning, in like speech, like natural language, like many other applications, you actually, look at the way you do kind of learning. They use some very similar technical dynamic programming for, just like Q learning in deep reinforcement learning, right? So, many people in the companies just keep telling me who are doing natural language processing. They say, "Wow, is there any similar technology?" And then it turned out that there is a similarity, but it's only ostensible. It's on the surface they look similar, in terms of how things systems are built. But in essence, in terms of motivation, they're very, very different. And the difference in that one, in reinforced learning, this Q learning actually plays a role of having this what's called the credit assignment over long distance. So it's a way of spreading out the supervision, the teacher information into, from the distance to the current one, like, playing, when you play chess, when you play, for example, Go. So the information is very, very far away. Like, you have to play about 100 some steps in order to know which one is win, which one is lost. And then when you go back to the initial stage, you don't have much information. It's very, very sort of diffuse information and how to get information back from the final win or loss into the current stage. And that uses, what's called the Q learning, or like playing some other kind of games. And whereas the dynamic programming for structured supervised learning actually is a very different motivation. And some of the techniques are in common though. So it's actually making efficient alignment for matching sequence target. And that has a completely different motivation, although the techniques are similar to each other. And that, so both of those are using different ways of dynamic program approximation. And one is much more sophisticated than this one. This is pretty easy, actually. We have been working there for a long time. And one needs exploration and the other one doesn't. Okay, so this is a very quick note for those of you who actually study this area. So now the final topic is what's called unsupervised learning. So the essence of the unsupervised learning, I'm just going to recap for those of you who came late in my introduction, is this is just, I believe that the major impact of unsupervised learning is, in practical applications will be in this area rather than in these, areas of, clustering, understanding data structure. The other area, somehow you have to define exactly what they are. Right? And this one has exactly the right definition. I want to solve the same problem as supervised learning, but I want to save all the cost. Right? And that's really has invaluable practical implication. So, the problem, the problem statement is that if you don't make input-output samples to match each other, how are you going to do the learning? Number one, deep neural net just cannot be learned right away, right? Very easy, very straightforward. If you look at the backpropagation objective function without the pairing, you just couldn't even learn and how to do that. And that's kind of the topic I'm going to spend a few minutes. And there's a huge practical benefit. There's no cost to create training data virtually. And both input and output data can be found naturally. Just like when I talk, this can be used for training. Okay, when you read an article written by somebody else without having to have the annotation as to what class it is, and that can be used for for deep learning. And the current technology does not allow that to happen yet. And that's sort of what I would say the frontier of the research in deep learning. For example, you can use millions of hours of speech for speech recognition. You can use millions of hours of video for video storytelling, and you can use all image in the web for image captioning, which people now have to label. It is impossible. So for the COCO task, the one Microsoft devised for this image captioning application, I won't tell you the number of dollars we spent for the labeling. We only come up with about $250,000. It costs all the money. And now it's only about less than 1 million, but here you can it's all the possible, all those makes it more, etc., etc. Now there's no free lunch, okay? And that's exactly what why it is important to do research. Right? So a lot of people in traditional machine learning, they don't like deep learning because they keep saying that there's no theory, there is no no bound, etc. But once you look into this important problem of how to do learning without matching the label, there's just a huge sort of space open for the fundamental research. And that's why we call it no free lunch, if you want to succeed in the goals that I just spelled out earlier. And this is a major frontier for deep learning. So our approach, so I'm not going to say much about it, so a lot of research is ongoing. I'm going to show you a little snippet of the example to show you how important the problem is and how difficult the problem is. So our approach is that we need to integrate diverse sources of world knowledge and application domain knowledge into a single optimization framework in order to solve the problem. So these knowledge sources will include that there are more and more. The more we actually look into the problem, the more we feel like that the knowledge is important and the framework is important. The optimization problem is important, and the optimization problem is actually turned out to be much more difficult than the one that we have been using in deep supervised learning. So those, one of the sorts of information will be how to use the prior information about the output statistic and structure. For example, for example, how do you make use of the structure of the language as the output to guide you through for translation and for for speech recognition and for image capturing, etc. And that kind of knowledge so far has not been used so effectively. And then, of course, you also need to use strong input statistics and structure, and that's what traditional unsupervised learning is referring to, and that's too limited. In order to solve the really big problem, we need to integrate all these sources together. And for those of you who actually have been doing a lot of good machine learning in the past, outside of neural network, you actually can make use of that big contribution in this area, in this unsupervised learning area. And the relationship between input and output, and also relationship between the input output from different domains, like transfer learning, and becoming one of the, not the only, but one of the sources, knowledge sources that can help reinforcement learning to succeed. And also another thing is called distributional properties of input and output sort of sequences. So this is the knowledge source that Facebook has been pushing. That's only one of them. Okay, I do believe that we have to integrate all of them, not just one of them. And I'm going to show you some of the example as how what kind of the problem, the nature of the problem we have been encountering so far. So let me elaborate some of the recent work we have done in this area, and just one of the sources. Okay, 5 minutes. Okay, So the way you actually can exploit the output statistics and the structure is to say that, well, you don't have the input-output paired, right? Then how do you do backpropagation? And just if you look at it literally, there's no way you can do it. And then now we have good statistics, we good Bayesian methods. So number one, we simply say that, so this is the cost entropy in the standard without the expectation. So if you don't have probability, all these statistics really come into the picture if you want to solve unsupervised learning problem. So if you don't have the paired x and y, okay? So this is, there's a little trick here. If you are dealing with the standard like image in that kind of application, it's very, very hard to do unsupervised learning because the output prior is so weak. It's just, but on the other hand, if you are solving structured prediction problem, the prior is much, much stronger, like a language. You actually have hope to make a progress. Otherwise, I personally don't think that hope is high. So that's why, in this, actually, this is the paper that we just submitted to archive. So if you get more chance, if you have an opportunity, you should probably take a look at. So this is like cultural entropy, okay? So if you pair x and y, just use cultural entropy, you get all the breakthrough, like speech recognition and image recognition and whatever, in the translation I talked about earlier. But if you don't have that, what do? Don't worry, use the statistics, you take an expectation of this, okay? So that's the best you can hope to do. Right? If you don't have any direct observation, you understand the statistics and maybe take a mean. And I think down the road, we're going to have higher order statistics in order to characterize the objective function. And rather than using cost entropy directly to optimize, which is what backpropagation is good, you take expectation. Once you do that, you just don't have the standard backpropagation you can do anymore. So what you do is that, so going through the mathematics, it actually turns out that you actually have, these interesting terms. So what it is that you sort of, using the probability, it's kind of language model, for example, in the sequence prediction problem, kind of to replace your original label. And of course, that's not very good, right? And then you take expectation of this whole thing as one of objective function, and that's one way of doing that. And then I'm going to show you that this is hard to work. You need to have quantum computing to solve the problem. I'm going to show you some example to show you that. And then you have to use some sort of generative model, another way of regularize the problem, using other sources of language. And if you embed that knowledge into your objective function to do gradient descent, whatever method you are doing optimization, you actually can solve partially the problem. So this paper actually shows some detailed experimental experimental setup for doing this kind of work. And this is the kind of basic result I show you. So one way, I don't know how many of you have read this. I think last year, Yan LeCun has a very nice paper about looking at the landscape of error surface for deep neural network, right? And then the conclusion is that there's a lot of saddle points rather than global optimal problem. and also there are lots of local optimum. It turned out that one local optimum is not as bad as the other local optimum. So there are tons of local optimums. So therefore, even if you don't get global optimum, they are not too far away from each other. And that's completely different than unsupervised learning. Now in unsupervised learning, so this is, we did some simulation, study in that paper. My colleague and myself, we have a team of people working on this. So if we actually can do some simulation, you actually understand exactly what global optimum is, and that's the this is the parameter space. So we compress big parameter into one dimension, so we can show the result. So this is a parameter space. T, one dimension, just map everything so I can show them. Ideally, I should show about 2 dimensions, but anyway. And then this is the error surface. So rather than deep neural network error surface is like this, they're all similar to each other. So even if you don't get global optimum, you're kind of getting into one of reasonably good local optimum. That's why you can get success. But now it's a completely different story. So global optimum looks like this, and then we found in many cases that near the global optimum, and there's some really big barrier that prevent the learning to get into here. So therefore, if you initialize your model somewhere here, like random initialization, just like in deep neural network, you'll never be able to overcome over here, right? So I make a little bit joke, funneling effect, right? So you might want, if you have this quantum computing, you might just go through here all the way. That's why I show this where somebody make a comment. So actually, last week I was visiting D-Wave, taking my high school kids to, to do some education in Canada, and they did. And I showed them, we just submit that paper. Oh, they're so excited about this one. They're very, they host me there. I said, no, don't worry about this, is a joke. So the error curve looks very, very different from what the standard neural net looks like. However, if we add this regularization embedding one aspect of knowledge that I showed you earlier, it actually, this sort of, it becomes something like this. Therefore, if you initialize something here without quantum computer, you might have a chance to get to global optimum. And then we're doing, this kind of exploratory study to try to understand the nature of the problem. So this is, similar to the status of supervised learning, deep neural network, like 20, 30 years ago, where people simply write a paper saying that how difficult it is to do neural network learning, right? So like Yasha Benjo wrote a paper in 1995. The title is why recurrent neural net is so difficult to learn, right? And they never got any solution, but we hope that we can get a solution for deep unsupervised learning through this kind of exploration. And this is another example similar to, so we produced tons of examples to demonstrate that the difficulty of unsupervised learning, it's so much harder than supervised learning. 1 minute, and that's, I think, pretty much what we have. And this is the final slide I'm going to show you, that there is a sensitivity. So in all these results that we have done, we have to assume that the model is perfect. It's just like a control theory, right? You have Newton's law, you understand. Even under the perfect condition, you have this problem. Now, if you don't have the perfect condition, you have this model mismatch, and that's this simulation show you that. So this is we added the noise into our simulation to show that model doesn't match with the real data observation. This is coming back to the real world now. And we can show that the problem become even worse. And we are looking for some solutions to make that happen, to solve this problem. I think that's all we have. Thank you very much.
Yeah, I just have a quick question.
Sorry. Yeah.
Thank you, Dr. Deng, for the nice talk. Now, I'm not sure I fully captured your title. I remember your title said that two types of big data.
Yeah, so you
I think we understand what the 3 styles of things are. What did you exactly mean by the 2 types?
Okay, so I had one slide. So right after that, the slide. Did you come late or no? Okay.
Probably,
so,
yeah.
Okay, so 2 styles is that the first style is that you have a match input-output data. That's one type of big data. Okay. And that's what everybody is doing now. And the second type of big data is you have big data, but input and output have to be separate. I mean, no, it's not separate. I mean, naturally separate. And the real issue is that how are you able to make use this kind of data, big data, to help you to do all the tasks, prediction tasks. And that's the one that I refer to. Yeah. So basically, one big data is designed to solve supervised learning problem, which has been very, very successful That's what you see. Why? You know, everybody's sitting here. Like 20 years ago, actually, I also did neural net 20 years ago. You know, about 5 people, you know, talking, sitting here. But now, you know, there's so many more people, and that is due to the availability of this big data with the match. Now, the next wave will be the other type of big data. Thank you. Yes.
I'm just wondering whether the reinforcement learning could be thought of as you're trying to model your, you essentially are modeling your teacher. You might have a
Correct.
model of your teacher, and you want to be getting rewarded.
Correct.
And so you build an internal model of your teacher that's going to provide you basically with
Correct. That's one way
supervised.
to, yeah, correct. That's consistent with what I said.
Yeah, okay.
It's consistent with what I said. So essentially, the teacher is a very weak. You have to model. If you don't model the teacher, so reinforcement is somewhere in between supervised and unsupervised. Unsupervised is saying that I don't even have to go through the process to model the teacher. But for the reinforced learning, you need to have ultimate the teacher some way, right? Like playing game. You have to know who wins. Otherwise, you cannot, when you play each other, there's no information, right? So you have to have something like that. Now, for unsupervised learning, you may not even need to have that, but you need to understand the statistics of the whole thing. So it's a different way of thinking. But what you said is completely consistent with what I just said. So when you model the teacher, if not, you don't model it well enough, it's kind of noisy teacher. And that's why it requires even more data than supervised learning. Now, for unsupervised learning, I expect the amount of data will be even bigger. However, these data are free. That's why I think in practice, it's more kind of interesting.
Thank you.
Yes.
One last question.
Yeah.
So you have 3 types of deep learning models. I wonder if you can elaborate or comment, you know, what's the breakthrough from like last 20 years or 10 years in terms of, you know, in the past, you have the methodology, right? Many
Yeah.
years ago.
Yeah.
So
The
what's the
reason
breakthrough? Maybe it's the
Yeah.
big data, it's the parallel computing or whatever.
Correct. Yeah. So I fully understood. So this is the question that reporters ask me all the time. So the main reason why deep supervised learning was able to sort of make recent breakthrough actually due to 3 reasons. Right? Number 1 is that computer become much faster. Right? Like 20 years ago, people didn't even realize how it is. And the second one is that you have huge amount of data. And the reason why huge amount of data helps you to make the learning faster. I have a tutorial, about 3-hour tutorial last year. Actually, I spent the whole hour analyzing this. And to summarize the point, it is that when you get a very deep network, especially in the recurrent network, LSTM, you get many layers, many steps, the gradient really vanish quickly. Every time you do, one, step of credit assignment, you lose something. And the big data helps in a way, but there are about 6-7 ways of solving that problem. And people actually found that by accident. I mean, the first way to find out a solution was what's called the pre-training. And Professor Jeff Hinton, he actually initiated that this paradigm. It's very useful for small data. And then we actually at Microsoft we found that 2010. After we worked with him for a while, we realized that we get more data. I mean, this is also by accident, right? So our product team, they don't really like, pre-training, right? DBM, what the heck of it, right? DBM, RBM, they don't even know what it means, right? So, we're just trying to explore, whether we can replace that using, sort of easier technology. And then when the data become bigger and bigger, and that problem automatically disappear. And the reason why it disappeared, there's a very good explanation. It's just you're staring at the backpropagation, formula 10 minutes. You probably can figure it out. And that's actually one of the points. But when you explain it, it takes the whole hour to explain. So this is the second factor. And the third factor is that people really sort of understood that the representation for the real world problem cannot be just simply be done in the very sort of naive representation, like in the shallow representation. And that actually came from, I have been working on speech for 20-some years. And so every time you look at the speech problem, you really think about the detailed representation of your data. You can't not simply just look at it. You get the data, use the Gaussian mixture model, and then you use hidden Markov model to make it. It just doesn't make sense. So a lot of my work, before deep learning, is actually to model, many layers of representation through generative model. I mean, for example, for speech recognition, the higher level will be the concept that you want to say, right? And then the middle layer would be something like motor control, exactly how the motor system is programmed by the concept, and that drives the muscle movement, right? And the muscle control. And using muscle control, you actually drive the articulation, and then from that you generate the sound. And we've been working on that for many years. And people understood that doing practical applications like image as well, it really just couldn't be very simple shallow representation. And a lot of machine learning people have this idea for many years, and then it just happened that for neural network, everything fit very well for GPU computation. I mean, for generative model of Bayesian network, it's very hard to make use of sort of GPU, fast GPU computation to speed up, to scale up this application. Right? So yesterday there was a tutorial, very nice tutorial on graphical model. You can see that after the whole 2 hours of tutorial, they only deal with the 2,000 units, right? And that's very, very hard to scale. And then for neural network, the scaling. I mean, the first time I started, doing deep neural net, number of parameters that I use immediately goes beyond 100 million, and that to me is small, and that was actually in 2010. So talking about 2,000 versus about hundreds of million, it's a many order of magnitude, and that sort of scalability is just immediate, rather than in other ways of looking at. So I think the third factor, and most people don't talk about this part, I think for the people who really think hard about the practical problem, to realize the complexity of the real signals and real data you want to deal with, and people realize that the deep representation is very important. I think that's probably, to me, is the most scientific way of evaluating why deep learning becomes a breakthrough. Thank you.
Thank you.
Okay.